We're fortunate. Rolf Opliger is our speaker today. And are you currently in Switzerland, Rolf? Or
Yes, I'm located in Switzerland right now.
okay. So I know you had been making a trip in the US at one point here, or we're planning on it. But Rolf is a longtime security professional, has written many books, several of which I know that I've used both as reference and in courses, particularly the ones on cryptography, and was fortunate enough. Rolf asked me to write the foreword to a couple of them, but he's been a scholar in the area of security, cryptography for decades. He's founder of a security consulting service. He's part of the Swiss National Cybersecurity Center. He teaches at the University of Zurich. Uh, many different roles, all senior roles. And we are very fortunate to have him joining us today. He's going to be talking about end-to-end encrypted messaging and some of the challenges and the future of that. So, without further ado, Rolf, welcome and please take it away.
Thanks for the introduction and thanks for having me. So the title, as Beth mentioned, is about end-to-end encrypted messaging. So things like Signal, WhatsApp, Threema, you name it, is going to be the topic of this talk. As Beth mentioned, I'm working for the Swiss National Cybersecurity Center for a company of my own for the University of Zurich, and I'm also running a book series for the US-based publishing company named Arctic House. So the outline of this talk is going to be brief introduction. What is the problem that we're going to try to solve? Then two solutions with different characteristics. One is the Signal protocol, the other is the more recent MLS protocol, mainly designed for group chats. And then I'm also going to talk about future challenges, conclusions, and outlook. Just for a full disclosure, I'm the author of two books on this topic. The left-hand book is about more general about end-to-end encrypted messaging, and the right-hand book is the one that's covering the Signal and the MLS protocol in more detail. So what is the problem? So the problem is very old, and this slide goes back to the Second World War when the Germans tried to encrypt their radio transmissions using a machine called Enigma. It was a mechanical device to encryption. And those radio transmissions, they were eavesdropped by some other intelligence agencies from Poland, from the British, and they tried to cryptanalyze those messages. So the story is very old. It's always the same story, and just the media that they change over time. Nowadays, it's no longer radio transmission; it's mainly the internet. But the setting is still the same. Somebody is sending a message to a recipient, and some eavesdropper are trying to illegitimately decrypt the messages. Now, the entire talk could be made on this slide. It basically gives the historical overview about messaging in the last 40 years, maybe. So on the right side, I've tried to, in some sense, characterize the problems that are solved. In the middle are the technologies that you can use to solve these problems. And the left column illustrates in some sense the key persons that came up with these solutions. So everything started with the invention of public key cryptography in the 70s, and maybe 15 years later or so, Phil Zimmermann developed PGP software as a solution to solve the secure messaging problem in the asynchronous case, meaning the traditional case where somebody sends a message and this message is going to be received by somebody maybe a couple of days later. So it's not synchronous, it's asynchronous between the sender and the recipient. And Phil Zimmermann, he used this public key cryptography to develop this software named Pretty Good Privacy, PGP, which nobody uses anymore. But very soon after it, the IETF developed and designed standards for this type of technology, for this solution, for the secure messaging problem, and the solution was specified as secure MIME. This was the IETF version of this solution to secure messaging. So let's say this was somehow the generation one, developed in the 90s, using very basic cryptography, very simple cryptography. But these solutions, they had many problems. One of the problem was usability. So there's a bunch of papers starting with why Johnny cannot use this technology in some sense. So all those studies, they refer to the inusability of this type of technology from the user's perspective. It's not suitable for the large-scale deployment. So this was one problem. The other problem was that public key certificates were not yet ready, were not available on the market. Even the public infrastructure was not there. So everything that had to do with certificate was not ready. And simultaneously, people came up with synchronous types of messaging in the form of instant messaging, and PGP and ASMINE could be used for this type of communication. And it was also the case that the keys that were used were very constant. They did not change over time. And this meant if somebody was able to break a key, he or she could decrypt messages forever. So there was no protection in time. And also, if I signed something with my private key, so I provided a digital signature for a message, I could not later repudiate having signed that message. So there was no deniability available. So those were at least 5 disadvantages of PGP and ASMIME, and they were addressed in a solution with an instant messaging solution for the synchronous case of communication named off-the-record messaging, developed by Nikita Borisov, Ian Goldberg, and Derek Brewer. They came up with this technology in the early 2000s, and the solution was using a Diffie-Hellman key exchange to negotiate an ephemeral key to be used for this message, and then to periodically refresh the Diffie-Hellman key exchange. For those of you who are not familiar with the Diffie-Hellman key exchange, it's just a possibility for two parties to agree and negotiate a session key. Some fancy mathematics is going on there. So if I want to exchange a key with SPAF, we exchange messages. So I send my Diffie-Hellman share to SPAF, and SPAF sends his Diffie-Hellman share to me, and then we can both compute the shared secret. So if I send SPAF a message today, I can also send the Diffie-Hellman share for the next to be encrypted message. So with each message, I can also provide a Diffie-Hellman share for the next to be encrypted message. This way we can periodically and dynamically always refresh our keys. This is known as a Diffie-Hellman ratchet, and it was introduced by OTR as well. So the big game that was being introduced with OTR was the use of Diffie-Hellman key exchange instead of RSA, and to periodically, dynamically refresh the keying material by using this Diffie-Hellman ratchet. So people thought this is a nice solution, but it was a solution only for the synchronous messaging case. Why? Because if I want to exchange a key with SPAF, we have to be online, both of us. So it's not useful in the asynchronous setting. If I want to send a message today and SPAF is able to read it only tomorrow, then we cannot use the Diffie-Hellman key exchange. So the problem that was next on the agenda was the asynchronous case. So some sort of an asynchronous Diffie-Hellman ratchet. And also we want to have a property named forward secrecy and post-compromise security. This means if a key is compromised, if a long-term key is compromised, then any communication in the past should still be protected. This is meant by forward secrecy. So it's a protection in the backwards direction. So you want to have the communications in the past being protected, even if today my long-term key is compromised. And post-compromise security means protection in the future. So if somebody is able to compromise my key material right now, I still want to reestablish a new secure session with SPAF again. So in some sense, we want to heal the security again. This is meant by post-compromise security, and those were very legitimate requirements for a asynchronous Diffie-Hellman ratchet solution. So this is what the signal protocol is all about. It provides a solution for this asynchronous case. And the solution is basically built around a centralized architecture. So instead of doing the Diffie-Hellman key exchange on the fly, we can deposit our public keys on a repository. So I deposit my key on the repository, and whenever SPAF is ready to send me a message, he grabs the key, my public key, my public Diffie-Hellman share from this repository and do the key exchange. So this is quite a nice solution for this asynchronous property. And then they also designed two technologies that are going to be the center of this talk. One is called an extended triple Diffie-Hellman protocol, and the other is called a double ratchet algorithm. Both of them designed to provide those properties named forward secrecy and post-compromise security. So protecting traffic that has been sent in the past and that is going to be sent in the future. So this technology, this signal protocol was designed by Moxie Marlensbeek, which is actually an arch name. So it's not really called this way. It's an artist name, and Trevor Perrin. They developed this in the early 2010s. And it's being built into the Signal Messenger, Facebook Messenger, WhatsApp, Wire, Viber, you name it. Most of the currently deployed end-to-end encrypted messengers are using this type of technology. And it provides a very elegant and very efficient solution for the point-to-point case. So if two parties want to communicate, but it does not scale very well. So the next challenge on the right side for the fourth generation of solutions was group communication or group messaging. How to provide an efficient solution if more than two parties want to communicate and exchange messages with each another. And this is where MLS comes into play, the messaging layer security protocol that has recently been standardized by the IETF as a protocol that you can employ if you are using group communications. And the solution that is being used is the use of binary trees. As usually in computer science, if you want to bring the complexity from linear down to logarithmic, you use trees. And MLS uses a lot of these trees. So this is where we are now. We have this very solid solution named Signal in the point-to-point case. Whenever we go to groups, we use the MLS protocol. This is state of the art. So the next challenges on the horizon is decentralization and federation on the one hand. So all deployed end-to-end encrypted messaging services like WhatsApp, Signal, Facebook Messenger, Wire, and so on, all of them are centralized. And this does not match well the model we are used to when we are using email. Email is highly decentralized, and we would like to have something like email in this secure end-to-end encrypted messaging space. So this is ongoing work, and the other open challenge is related to metadata hiding. How can we avoid the generation and use of metadata to keep ourselves anonymous? So these are going to be the challenges of the future. So this is the big picture, and we would like to dive more deeply into the signal and the MLS protocol. So the state of the art in end-to-end encrypted messaging. So the signal protocol, as mentioned before, it's like off-the-record messaging just for the asynchronous setting, meaning we care about something like email, where the sender and the recipient need not be online simultaneously. And as I've mentioned before, the first part of the solution is to use a centralized server to deposit and grab from the Diffie-Hellman key shares. So this is visualized on this slide. Normally, you have the Diffie-Hellman key exchange on the left side, where A sends its public key to B and B sends its public key to A, and then they can both compute the shared secret. Now, in the asynchronous setting, we have a key repository. So when A wants to send a message to B in encrypted form, it grabs the public key from B from the key repository, and obviously B before that has to deposit its key there. So B sends its public key to the key repository where it is grabbed from by A, and A can then mount and execute the Diffie-Hellman key exchange using B's public key and its own secret key to compute the session key. A can then encrypt the message with the session key and send both its public key and the encrypted message to B. And now B can do the same Diffie-Hellman key exchange using the public key that he got from A together with its own private key. And he will compute the same session key, the same message key, and can use this key to decrypt the message. So using this key repository, we can also use the Diffie-Hellman key exchange in an asynchronous setting. But now there are these two key technology I mentioned earlier, the extended triple Diffie-Hellman key agreement or exchange protocol and the double ratchet. Now let's first focus on the extended triple Diffie-Hellman key protocol. Normally, when people do a key exchange, an authenticated key exchange like in OTR, they do the handshake. This is visualized on the left side, the handshake between small a and small b. So small a and small b are ephemeral keys, whereas long-term identity keys are visualized with a capital letter. So capital A is standing for A's long-term secret key, and capital B is standing for B's long-term key, identity key. So normally A and B do a handshake, a Diffie-Hellman key exchange with their ephemeral keys, and then they both sign their public Diffie-Hellman share to provide authenticity. So by signing their keys and doing the key exchange, they have what we know is an authenticated key exchange. So a normal key exchange together with authentication. And the authentication normally is provided by signatures. This is the normal case. Now, the invention of this extended triple Diffie-Hellman key exchange protocol is to replace the signing procedure with two other Diffie-Hellman key exchanges. Now, on the right side, we see this extended triple Diffie-Hellman key exchange protocol, and now we are doing three Diffie-Hellman key exchanges. The normal handshake between the ephemeral keys, but also handshakes between the long-term identity keys and the short-term ephemeral keys. By combining those long-term identity keys, we also get authenticity, but we only do Diffie-Hellman key exchanges. So the big advantage of this protocol is that there's no need for signatures, because signatures tend to be the computationally expensive operations. So we only use Diffie-Hellman key exchanges and still provide authenticity in some sense, by combining and putting in line the long-term identity keys. So this is the mystery of the extended triple Diffie-Hellman key exchange protocol. There are 3 exchanges going on, intermixing the short-term ephemeral keys together with the long-term identity keys to provide authenticity. So how does this look like in practice, or if we go into a real software? So assume that A installs the software like the Signal Messenger, WhatsApp, or Facebook Messenger, any software that supports the Signal protocol. What does the software do? Well, it first randomly generates many key pairs, so many public key pairs to be used for Diffie-Hellman key exchanges. And by the way, it's using elliptic curve cryptography using the curve 25519, but this is just an implementation detail. It's just an efficient possibility to implement the Diffie-Hellman key exchange. So for each entity, like in this case A, there are many key pairs involved. In fact, there are 3 types of key pairs. One is a long-term identity key pair. It's denoted like this, PKA. Capital A is standing for long-term, and ID, the superscript, is standing for identity key. P key is the public key, and S key is the secret private key. So A randomly selects an identity key pair. This is going to remain the same forever. This is just an identification key for A. But A also selects, or the software selects on behalf of A medium-term pre-key pair. So this is a key pair that is going to be changed maybe on a monthly basis. So it's medium-term. And the public key of this key pair, so PK subscript small a, and the superscript is to the power of pk, is standing for pre-key. So the public key of this key pair is going to be digitally signed with a private identity key. So in some sense, the identity key certifies the public key of the pre-key pair. And finally, there's a pool of n ephemeral one-time pre-key pairs. So these are key pairs that are going to be used only once. If one key pair is used, it's cancelled, it's removed from the stack. So there's a pool of n such key pairs, also generated by the software of A. So now we have n plus 2 public key pairs that are generated, and the public keys are all of them uploaded to the key server, to the key repository. And this set of n plus 2 public keys is referred to as the pre-key bundle for A. So each participant in the system uploads a pre-key bundle for it. And again, the signed pre-key pair must be renewed on a regular basis, like on a monthly basis, for instance. And the software has to make sure, or should make sure, that the pool of one-time pre-key pairs doesn't get empty. So whenever needed, this pool is refreshed and new key pairs are added to the pool. This is automatically done by the software. The user doesn't have to care about. So this is going on when A initializes the software. And now A wants to establish a session with B. So this is visualized, and on the right side and on the left side is the textual representation of this figure. So A wants to send a message to B, so it first downloads the pre-key bundle of B, basically downloading the public identity key, the public pre-key with the signature, and optionally, if available, one of those public one-time keys. So the index PKB, J is standing for the jth public key in this pool that belongs to B. So it's one of the pool, one element from this pool is randomly chosen by A and downloaded. And now A verifies the signature for the public pre-key, generates a public key, an ephemeral public key pair to be used for this session with B, and uses B's pre-key bundle to compute a master secret S. Now this computation is visually drawn on the right side. The upper figure illustrates what keys are being used. On A side, there is this identity key pair and the ephemeral key pair. And on the right side, we have B's key. So A is going to use the public identity key of B, the public pre-key of B, and one of the one-time key, one of the public one-time keys. So by combining those keys together, so A is taking its secret, its private identity key, combined with the public pre-key of B. This is the first line. Basically, let's see. This one refers to this first diffie-element key exchange. The second is built by A using its private ephemeral key, combine it with B's public identity key. This is the second diffie-element key exchange. The third is combining A's ephemeral private key together with B's public pre-key. This is 3. And the fourth is optional because we said A downloads a one-time public key only if one is still available in the pool. If there's none in the pool, then A cannot grab one. So this fourth diffie-element key exchange is only possible if one-time key has been downloaded by A. That's why this step is optional. Now we can concatenate those session keys that result from these 4 diffie-element key exchanges. We concatenate the results and we run some sort of a hash function for the result. This key derivation function takes those 4 ingredients and derives one session key from them. So S is the key that is derived from the concatenation of those 4 diffie-element key exchanges. And now A deletes its ephemeral private key. It's no longer used. After the diffie-element key exchange has been performed, the secret key is no longer used. And A also deletes all intermediate results. So all diffie-element outputs are deleted as well. This is only to provide forward secrecy in post-compromise security. If no intermediate result is stored on A's side, so nobody can compromise these results. So now A knows a secret and shares the secret with B. And A generates what we call associated data. It's an encoding of the identities of A and B. So AD equals the encoding of A's identity key, public key, together with B's identity public key. This is just to, in some sense, to add in clear text to the message what parties are involved in this communication. And then A can send its initial message to B, basically specifying the public identity key of A, the ephemeral public key of A, the index J that has been used to take the J's one-time public key from B's pool, and then sends the encrypted message together with its associated data to the recipient, which is B in this case. So there is quite a lot to do when A sends the first message to B. So this step has to be performed whenever A sends the first message to B, after its session key is established. And now what can B do? Well, B does very similar things. B extracts the public identity key of A and the ephemeral public key of A from this initial message. It has been added to this message as we have seen before. Then B loads its private keys from memory and does the very same Diffie-Hellman key exchanges that A did. Now B does it on his side, basically switching the roles of the public and the private keys. So whenever A used its private key, B now uses the public key. Everything else remains the same. This means in the end that this session key that is being computed by B is exactly the same as A computed in the first place. So B can also compute this associated data as A did before and can use S, the session key, together with the associated data to actually decrypt the message. And if everything is fine, B can also delete its intermediate result and use S in whatever comes next after this initialization step. If decryption is not successful, then well, something has gone wrong. So the protocol aborts and maybe an error message is sent back to A. So this happens in this very first step. And so far, we have not yet talked a lot about authenticity. So we have said that A grabs the public identity key of B from the key repository, but A cannot be sure that this is the correct identity key of B. It may be the case that the intermediate, the key repository, whoever runs this, tries to cheat, tries to invoke a wrong key. So this is where the security number comes into place. You may have seen this in Signal, in WhatsApp. Whenever you contact somebody new, you are required or you're requested to compare this QR code or the security number with your peer. So if I send a message to SPAF, then SPAF will see on a screen that this participant may not be trusted. So you better compare this QR code. If you both have the same, we can be sure that we really talk to each other. There's no man in the middle. So now this security number and the QR code, they basically represent this encoding of the public identity keys of A and B. If both of them see the same keys, then obviously they talk to each other. This is the rationale. Normally, this step is not performed by users. Users normally ignore this step, and this is a problem. And this is why WhatsApp, at least, has released a new concept, what they call an auditable key directory. So when I download B's key bundle, I also get a proof that this is really B's key. And the technology that's being used is something similar to certificate transparency that is being used in public infrastructures. I just want to make the point that there is an additional step involved here, that the user has to do something in order to defeat malware in the middle attacks. But again, this step is seldom done in practice. So now we have established this session key between the sender and the recipient. using this extended triple Diffie-Hellman protocol. We may have also verified the security number to be sure that we are really talking to the peers. So now comes the double ratchet algorithm into play. This is the mechanism that allows us to very dynamically, permanently refresh the key material. In the ideal case, we want each and every message to be encrypted with a new key. So we want to avoid the reuse of key material. And this is quite a complex technology. It's using something that we call a key chain. There are two types of key chains. The green one, let's call this a root chain, type 1. It basically takes a root key, takes some input from the left side, then runs a key derivation function to get a new key plus an output. And the output is going to be used in the further procedure. So the chain is you take a key, you take an output, you apply the key derivation function to get a new key, a new chain key, and an output. And you can iterate this as many times as you need outputs. The root chain, the green key chain, has this property of requiring an input value in each and every step. This is simpler in the red key chain. It's basically the same game. The only difference is that the input that's normally provided by the Diffie-Hellman key exchange is now replaced by a constant to make it very, very fast. So the type 2 key change, the red one, is very, very efficient. You take a key, you hash to get a new key, and the message key you hash to get a new chain key and message key, and so on and so forth. This is a very efficient operation. So you are going to use the green one to feed it entropy into the system, and you are going to use the red keychain to be very efficient. So let's put the things together. Now on the upper left, we have executed this extended triple Diffie-Hellman protocol to compute the session key, which is the root key for the green type of keychain, the less efficient one, where the input value comes in from the left. So A has executed this protocol, has established the root key, and wants to start this double ratchet mechanism. By the way, it's called double ratchet because there are two types of ratchets involved. One is the Diffie-Hellman ratchet. This is the green key chain, and the other is the normal key ratchet that's only using hash functions, basically. This is the red one. So we have established this session key, and now A wants to start the game. Well, A establish randomly selects an ephemeral public key pair and uses B's pre-key, public pre-key, to compute a Diffie-Hellman output value. And this Diffie-Hellman output value is fed into the key derivation function. I'm now here on the top of the slide. So this session key S is combined with the output of the Diffie-Hellman key exchange. Both of them are input value to the key derivation function. The output is a new root key and the output value. And this output value is going to start a very efficient red key chain. And this is part of what we call the sending chain. So whenever A wants to send a message, he grabs a new key from this sending chain. So he sends the first message, takes the first key, hashes, takes the second key, hashes, takes the third key, and so on and so forth. So for each and every message to be sent, A fetches a key from this key chain. Sooner or later, A and B are ready to start a new Diffie-Hellman key exchange. So from time to time, A will send a Diffie-Hellman share to B, and B will send a Diffie-Hellman share to A. So they are ready to compute a new Diffie-Hellman output value. And this will enter the second iteration of the root chain. And now they feed the receiving chain, and so on and so forth. So whenever they can do a Diffie-Hellman key exchange, they iterate the root chain and they start a new sending or receiving chain. This is the game that A and B are going to play. And obviously the A's sending chain must be in sync with B's receiving chains. So the sending chain of A is the same as the receiving chain on B side. So the two chains must be synchronized. Because if A encrypts a message with a message key, then this must be the same key that is used when B receives the message and wants to decrypt this message. This must be exactly the same key. That's why the sending chain on the sender side and the receiving chain on the receiver side must be in sync. Maybe less formally, more visually speaking, this is going on when you're using the Signal app or WhatsApp. So on the left side, there is one party, on the right side is the other party. Both of them have a Diffie-Hellman ratchet, have a root chain, a sending chain, a receiving chain. Each party downloads the pre-key bundle from the key repository, and then they do exactly this. So on the left side, the sender downloads the recipient's pre-key bundle, starts the Diffie-Hellman ratchet, the root chain as discussed before, and then feeds the sending chain, takes the first key, which in this case is this orange message that can be encrypted with the orange key, sent to the recipient, and the recipient grabs the same key from its receiving chain if you follow the protocol and can decrypt the message with this key. And then maybe the right side sends a message, takes the key from its sending chain, sends the green response back to the left side, and now the left side must grab the appropriate key from its receiving chain, and so on and so forth. This illustrates that the receiving chain and the sending chain on either side must be in sync. So this is quite complicated, but works fine in practice, is very efficient if two parties want to communicate. It runs well. But it has the problem that you always have to establish those channels between two peers. If you have a group, there are many channels to be fed. So there's a scalability problem here. And this is where the IETF founded this messaging layer security working group that came up with a protocol of the same name. It's specified in the appropriate RFC. It's a official standard now. You can use this if you run a group. And again, without going into the details, it's using binary trees to manage the state of this group, bringing down the complexity from O of n to O of log n. So this is very efficient even for thousands of participants. But there's a problem here that's beyond cryptography, and it goes back to this quote of Benjamin Franklin, who said that three may keep a secret if of them are dead, meaning that it's very, very difficult to keep secrets in very large groups. This is obvious. We know this from daily life. The more participants in a group, the less likely it is that the secret is going to remain secret. So the usefulness of encryption in very large groups is questionable and remains to be seen in the field. So we have a technical solution for these group communication problems, but we are not so sure whether this is really useful in practice, because there's no big use in encrypting group communications for groups of thousands of participants. one or two of them will leak the secret. Probably. So this is an open question beyond technology. Now, maybe future challenges, what needs still to be done? As mentioned before, one question is decentralization. All messaging services and encrypted messaging services are centralized. And this is a problem today where we talk a lot about data sovereignty. This is a big issue, not only in cloud, but also in end-to-end encrypted messaging. So how how uh, how do you provide sovereignty if the architecture is centralized? This is quite a challenging research question. And the model to keep in mind is email. We would like to have something like email where everybody can run an SMTP server. It's no centralized architecture here. It's highly decentralized. So it's something completely different than WhatsApp and any of the commercial available end-to-end encrypted messaging services. So how would this look like? This is quite an open question. And the other open question goes back to this quote of General Michael Hayden, who this famous quote in which he said that they kill people based on metadata. So metadata is very useful from an intelligence perspective. So it may be interesting to avoid or at least hide this metadata. And again, this is very difficult if you have centralized architecture. How can you provide, or how can you protect or hide this metadata if there's only one entity running the service? Sounds to be very difficult. And also there is little incentive to actually hide metadata. So all business models around end-to-end encrypted messaging are based on collecting and providing and selling metadata. And hiding works against these interests. In one way or another, it requires to use some anonymous networks like Tor, for instance, the onion routing. The onion router network is one possibility, and one solution that's built on the top of Tor is named Ricochet Refresh. So this is one possibility to hide metadata. And again, research challenge to find other solutions. Now I'm already a little bit late. I try to hurry up. So conclusions and outlook. So end-to-end encrypted messaging has a very long and eventful history. Remember this initial slide summarizing the history going back to the early 90s. So this was actually the time when I also entered the field. So I grew, in some sense, I grew up with PGP and I survived all those 4 generations. It's a very long story. And nowadays, the field is entirely dominated by the signal protocol. There are only a few exceptions. The 3 most important ones are listed here. Is iMessage from Apple is not using Signal, at least not yet. Threema is also using a proprietary protocol as well as Telegram. So these are 3 prominent examples that are not using Signal. Most others do. Most other end-to-end encrypted messaging services, they use the Signal protocol. And all of them are trying nowadays to make their solutions resistant against quantum computers. So they build in some post-quantum cryptography in a hybrid fashion, meaning that they are using Diffie-Hellman key exchange as well as technologies that are resistant to quantum computers. And Signal, for instance, the solution of Signal is named post-quantum extended Diffie-Hellman, PQXDH, and the solution of Apple is named PQ3. All of them combining traditional cryptography with post-quantum or quantum computer resistant ones. Now, another thing to keep in mind that is that end-to-end encrypted messaging refers to the security of data in transit. So when data is or messages are sent from A to B, they are protected. But what happens in the endpoints? What does the recipient do with these messages? Well, very likely it's going to be stored locally in the clear or maybe in the cloud. And what can we do then? Because it's very likely that if somebody wants to compromise those messages, he or she is not going to break the cryptography. He or she is going to the cloud and ask for the messages. This is where two solutions come into play. One is the use of self-destructing messages as pioneered by Snapchat. So messages have a limited lifetime. Sooner or later, they are deleted from the system. And if something does no longer exist, it cannot be compromised. So this is a very radical solution. And the other solution is the end-to-end encrypted backup. So keep the messages in encrypted form in the cloud, but in a way that the cloud provider cannot decrypt the messages. This is the goal of end-to-end encrypted backups, that you are the only person who is able to retrieve the key needed to decrypt the backup. And this is a technology that's being pioneered by WhatsApp right now. You have this possibility in your app. Finally, end-to-end encrypted messaging is not only a technical problem, so it has some very interesting technical dimensions, but it has also social, economic, and political issues and implications to consider. And this is a very important topics because the crypto wars, they prevail, and the crypto wars refer to the possibility of intelligence agencies and police forces to be able to decrypt your messages, even if they are end-to-end encrypted. So the police forces that would argue that they need to have this feature, this possibility, and you as a consumer, you don't like the police to have this possibility, so you would likely argue in favor of end-to-end encryption in a way that nobody except you is able to decrypt those messages. And those wars are going on and on. Maybe it's the fourth or fifth incarnation of this war that we see today. So countries that try to outlaw the use of end-to-end encrypted messaging. And the argument is always the same. If criminal people want to encrypt, then police forces need to have a way to decrypt those messages. More or less always the same argument. And this is a political question, whether you think this is a good idea or not. Personally, I don't think so, but there are arguments in favor of this possibility as well. So this was, in a nutshell, what I wanted to say about end-to-end encrypted messaging, and maybe we have questions. I'm actually not able to see the Q&A section.
As a reminder, if you have a question, please post it in the Q&A and we'll access it there.
Yeah, maybe I can get started while possibly some other questions may come. Uh, All right. So yeah, Rolf, really very exciting talk. It's very nice to give such a complex information that you're able to present in a very informal manner. So thanks a lot for that. Uh, the question I wanted to ask was when you look at the post quantum security. I think it's fair to say that all the properties that we want, the property that you listed on your second slide, we can achieve them already in the post quantum world, right? With this hybrid with the like basically Apple's iMessaging services that they introduce, or as well as the signal standard they're working on, we can achieve all the properties. Is that a fair statement to make?
Yes, yes, we can. So it's almost solved. Let's put it this way. We can complement those Diffie-Hellman exchanges with what we call a KEM, key encapsulation mechanism, that is post-quantum resistant. And if we combine this, we get some notion of security against the effects of quantum computers.
Mhm.
The only thing we haven't solved is the authenticity part, but this is considered to be less pressing, let's put it this way.
Yeah.
So if we want to have a notion of post-quantum ready type of authenticity, this is not yet built into the products. This remains to be done. But authenticity is not so a big problem because what you fear about quantum computer is somebody storing data today and decrypting it tomorrow in a moment when he or she has access to a quantum computer. Now, authenticity is about real-time characteristics. If I send a message to SPAF, I want now to be sure that this is SPAF. So authenticity doesn't have this long-term characteristics. That's why we assume that we have more time on this side. So let's put it this way. For the moment, we have a very good feeling about the security of our solutions, even in the case that somebody is able to build a quantum computer tomorrow, which honestly speaking is not very likely, but we will see.
Thanks. Yeah. So indeed, except for harvest now, decrypt later, I guess authentic, that's not the problem there. But cryptographically, it's solvable still, right? It's just that it's not yet included in the product.
Yeah, sure. There's a long way to go to include it into the products. I mean, people are working on this front. They are trying to integrate those post-quantum algorithms into the currently available protocols, mainly the Signal protocol. But it's a long way to go. There are some interesting engineering questions to solve to make it as efficient as possible. So it's not that easy, but it's solvable, and people are working in this direction. So this is not going to be the major problem in the future, I guess.
So just to last on, so you touched upon the efficiency. So how much is the overhead as compared to the pre-quantum secure systems that we're currently expecting with the new post-quantum solutions?
I mean, the post-quantum solutions, they are quite efficient. The keys are a little bit longer,
Mhm.
but this is not a big issue. The encryption and decryption operations, so the crypto operations, they are fairly efficient. So let's say if I have to mention a number, then I would say it's not more than doubling the workload, something like this. And this is very efficient. Because keep in mind that this triple Diffie-Hellman protocol means you are applying the Diffie-Hellman key exchange 3 times. So, and you are not going to recognize it when you run Signal or WhatsApp. It's being done on the fly. So contemporary cryptography is very efficient and it doesn't slow down the performance of the products significantly. Even if there is a factor of 2 or 3, you are not going to recognize this. This almost runs in real time today. This is different than 20 or 30 years ago.
Yeah, I would just add as an observation, um, this is one of the aspects that 30 years ago we had smaller key sizes because it simply took too long to do the encryption with longer key sizes. And then, of course, as machine capacity got bigger and some algorithms got better, we had to deprecate like DES as an example, actually the DEA, but the DES, because it was now tractable to do brute force searches. And we've moved now into a realm where we have much greater confidence that even faster equipment isn't going to do that for us. But the protocols are now taking the extra time rather than the actual encryption decryption, because we have the rounds of the protocols. And that may change too with time, but these are all economic decisions. These are policy decisions that we have to make, just like the key escrow aspect is not a technical decision, it's a policy decision that we can't really solve with technology. Uh, we've come up with some
Yeah.
very good technology, but it's often at the mercy of the people who have to pay for it or the people who have to regulate it.
That's exactly the point. Many of these open issues are political ones, and they cannot be solved technically.
So this is one of the things that has come up repeatedly in the seminar series, some of our courses and CERIAS itself, is that if we really want to explore the space, we have to think more broadly than simply the technology. Um, we can do elegant things in technology, but ultimately we have to deal with people. And
Fully agreed.
yeah, sorry, go ahead.
No, it's fully agreed. This is exactly the point. All this technology, it must serve the people. And if people cannot handle this, then we have lost anyway. So all this technology that must be built into the products very transparently. So the user should not recognize it. And this is the big advantage today. If you are using WhatsApp, everything is transparent. You don't recognize it as a user. And compare this to PGP, which was actually a user nightmare from the
Yeah,
usability perspective. And this has changed fundamentally. So nowadays, cryptography is built into the products in a way that users don't necessarily recognize it. This is very good from a security perspective.
it it is, but then there's a burden somewhere there for the user to verify that the technology is in place and is working and is appropriate.
Sure.
There was an article that appeared, I think, today about how Chinese AI companies provide weaker versions of the security solutions to organizations contracting with them that are in disfavor with the Chinese government, but the solutions are technologically complex. They're AI solutions, so the end users don't know. Sort of like what the crypto AG machines, right, is that they were assumed to be working well, but people didn't have the expertise to know that they had actually been backdoored.
I
So
fully agree. This
yeah,
is
we
again,
have great challenges in security to balance both the complexity to be able to do it right and also provide assurances through to the end user that we are actually acting in their best interest.
yeah, the more transparent the technology is, the more difficult it is for the user to recognize what is going on. If the machine is working properly, this is very difficult. If the cryptography is very transparent, then there is this disadvantage that the user cannot check whether it is working properly.
So for some of the students who are listening in, maybe this gives you a hint as to some areas where some research could still be used and could be helpful. We this has been wonderful. Thank you, Rolf. It is great to hear you in person and on such an interesting topic. I think many of us use these protocols on a regular basis, but haven't really thought about what goes on beneath the hood, as it were. Uh, and I hope we have a chance to welcome you in person sometime in the near future.
Yeah, would be great. And again, thanks for having me for this talk at least. It's
So
been a pleasure from my side.
well, that's wonderful. And for all those who've tuned in, please tune back in next week. Again, we will have one of these talks next week. I'm not sure who our speaker is next week, but it should be somebody interesting as well. And everybody enjoy the rest of your day.
Yeah. Bye. Thanks a lot.
Bye bye.
Bye.